So the assignment that is due today is 2.3, and 2.3 is on continuity. Any guesses what I mean by this word continuity? Riley, any ideas what I mean by continuity? Okay, well, we're talking about limits. And so, well, the idea of continuity comes from the word continuous. And you might remember back in, I don't know, secondary math 1, they talk about discrete versus continuous. And a very unrigorous definition of continuous is that you draw a line without lifting up your pen. That'd be a non-rigorous example or a definition of continuous. So continuous is a curve drawn with a pen without lifting it up. So for example, this is continuous. In fact, specifically, it is continuous from this point right here to this point right here. From point A to point B, it is continuous, meaning that all of the infinite fractions in between would be included as well. Not just, I don't know, not just 1, 2, 3, 4, 5, and 6. We're looking at all of the infinite fractions in between that would be included. Now, if we wanted to make this definition more rigorous, we would have to add something like, say that we have some line. So we have a line drawn from A to B. And so we have a line drawn from A to B. So I have this line right here. Here's A and here's B. With some value C in the middle, with point C somewhere in there. It doesn't matter. C could be here, C could be here, C could be here. I don't care where C is. There's just some value of C in there. Now, in fact, C represents all values in there somewhere. Then, you know, so that let's draw this, let's do the limit as X approaches some value of C of our function. We'll call this function f of X. We'll say f of X equals f of C. Yes. Yep, that's fine. All right, so what does that mean then? How do we interpret this right here? The way that we interpret this for our function of f of X is that, in fact, let's do an example. Let's do, here's an example. I have, let's do y equals 2x plus, let's do f of X. F of X equals 2x plus 3. Now, if C is some value, I don't care what C is, it could be anything. We'll say that it is, I don't know, it'll be 3. So is the limit in this case, where is the limit as X approaches, I don't want to use 3 because 3 is already used there. What if we say the limit as X approaches 1 of our function, that's going to equal what? As X approaches, gets closer and closer to, and maybe it'd help instead of writing it. Oh, let's just leave it that way. When X gets closer and closer to 1 for this function, what does Y approach? Yeah, we just plug it in, we get 2 times 1 plus 3 gives us 5, so it's 5. Is f of 1, is that 5? Yeah, so this is continuous. It's continuous at the point of C. It's continuous at the point of C. Let's do another example. What if I have something like this? I have my function is x plus, let's do a more difficult one. Let's do x squared plus 8x plus 15 over x plus 5. Now, I'm looking at is the limit as x approaches -5 of our function of f of x. What does that equal? Well, how do we find the limit for this? Does anybody remember how we find the limit of this? Nobody remembers? Can we find the limit by factoring? What if I factor the numerator? What do I get? X plus 3 and x plus 5, yeah, over x plus 5, all right. So what do I do? Yeah, we just cancel this out and I'm just left with x plus 3. And now there's no violation to plug this in, right? So what's the limit as x approaches -5? It's -2. So does that sound right to you? Okay. What is f? What is f of -5? Louder? It doesn't exist, yeah. So is, based upon our more rigorous definition, is this equation continuous at x equals -5? No, it's not, because they're not the same. In fact, we can graph this. I don't know if this would help to graph this. Let's go to Desmos. So I have y equals x. Let's make sure we have a numerator and denominator. X squared plus 8x plus 15 over x plus 5. And if I go over to -5 over here, we see that we have a hole in our function right there. So we approach, if we go to the other side, we can see that we are approaching -2. When x approaches -5, our y approaches -2, but f of -5 is not -2, right? No, because there's a hole there. So we say it's not continuous at the point. So that's our more rigorous definition, to say that if the limit as x approaches that value is equal to f of that x value, then it is continuous at that point. Right, so, all right, if we're going to be talking about continuity, we should probably talk about discontinuity. In fact, there are 4 different types of discontinuity. Let's talk about these 4 different types. Here's the types of discontinuity. The first one, if I have a graph that looks something like this. We say that this graph is discontinuous at some C value here. and it's discontinuous because of infinite discontinuity. We can see if we approach that C value from, say, the right-hand side, we approach it from the right-hand side, we can see we go to negative infinity. And when we approach from the other direction, we go to infinity. So the discontinuity is called an infinite discontinuity. This is called infinite discontinuity. Our next one looks something. Hey, Sasha. It's all good. This is called, now notice there's just a single hole in this graph, which means that if I could replace that hole with one single point, it takes care of the problem. This is called point discontinuity. Point discontinuity. And actually what's more common is removable. It's called removable. Removable discontinuity. Discontinuity. I'm going to circle this because I see this in the IB curriculum. The questions that are on the AP, I call it IB, that's the International Baccalaureate. The AP curriculum. In the AP curriculum, the questions that I see on the AP test, they use removable discontinuity much more than they use point discontinuity. So I'm circling it just because that is the more common verbiage that they use. Okay, so we have point discontinuity, we have infinite discontinuity. There are two more. Another type is if I have something like this. This is called a jump discontinuity. Getting sloppy. Jump discontinuity. And then the last one. You want me to wait to get, so you guys get caught up? So far we have an infinite discontinuity, we have a point discontinuity, we have a jump discontinuity. When you look at the discontinuity, Riley, how would you be able to identify an infinite discontinuity? What tells you it's infinite discontinuity, not something else?
Well, if the approaching value approaches the vertical asymptote.
Yeah, if your values approach these the vertical asymptote in opposite directions, right? What if you're going together? What if you go together?
That would still be considered.
It's still a discontinuity, yeah, because there's still a hole in there. So where if, for example, if I add 1 over x squared, x cannot be 0 still. And so there's still a discontinuity there. And because you're approaching infinity, it would still be an infinite discontinuity. All right, by looking at this one, Kata, right here, what would tell you that this is a removable discontinuity? Yeah, if I took one single point and I put it right here, then that takes care of the problem. There's no more problem left and there's no discontinuity. Eleanor, what about this one? What about a jump discontinuity? How is a jump discontinuity different than an infinite discontinuity? How are these different, this one and this one? Well, here's a point on the graph that's part of it.
Oh, yeah, sorry.
And here.
Well, there's not really vertical asymptote.
There's no vertical asymptote. Yeah. What if I made it? Would this be any different if I made made an open circle here? Oops. No, it's still a jump discontinuity, right? It's still a jump discontinuity. So what defines a jump discontinuity compared to an infinite discontinuity? Miguel,
With infinite discontinuity, it has two lines that it's stuck in between two that go infinite both ways and critically, and with jump it has 2 points.
yeah, if I actually, how long would the line be? How long would my line need to be if I decided to connect this point here to this point down here?
Infinite.
Yeah, it'd have to be an infinite length. It'd have to be an infinite length to do that. What if I connected these right here? That's going to be finite, right? It's going to be a finite distance. I had a student yesterday that said the way that she described it was to teleport. It looks like you're going along here and then all of a sudden you teleport over here. Whereas up here, you're literally going to, I mean, you're never stopping here. Here you go to a stop and then you start again over here. Here you go all the way to infinity. You never stop. You just keep on going up. And then there's another piece over here where you're down here at negative infinity and you continue over. So they're distinctly different.
If the latter is the line being a gradual change, then how small can that distance be for it to be considered a jump?
As long as it's more than one dot. As long as it's more than, if it's one more dot, if it's more than one dot, then it's not a removable discontinuity because you'd have to fill in 2 dots, right? So because of that, the best you can do, it's not removable anymore. It's a jump, to jump from one point to the next. All right, the last one. The last one is called an oscillating discontinuity. Oops, wrong tool. It is called an oscillating discontinuity. What does oscillating mean? What does oscillate mean? Yeah, like a pendulum, like for a grandfather clock, for example. Periodic functions are oscillating too. They go up and down, up and down, up and down. And that's sort of the point of this oscillating discontinuity. What happens, say that we have this periodic function like this, and then all of a sudden it comes in here and then it just goes up and down, up and down, up and down, up and down like this, like that. You don't even know what's happening in there anymore. Let me try that again. So we have this graph that's going along here. And all of a sudden, it just goes up and down, up and down. It oscillates so much here. We don't know what's happening in here. We don't know what we're converging on. We don't know what we're converging on. Let's look at this, for example. Let's look, I can't talk today. Let's look at some examples of these. All right. Here is my first one. Y equals 3x over 2x plus 1. Does this graph have discontinuity? Actually, let's change this. Where does this graph have discontinuity? At x equals what? -1, yeah. If this x right here was -1, then you have a -1 plus 1, which is 0 in the denominator. X cannot be -1. So I have x equals -1. X cannot be -1 for this graph. That's why we converge on that vertical asymptote. What kind of discontinuity is this? It's called an infinite discontinuity because the two are converging, one to infinity and the other to negative infinity. Yep. All right, so what if I had something like this? I have y equals 3x minus 4. I actually want all that over. X minus, let's do this. X squared minus x minus 20 over x minus 5. Where is the discontinuity? Where? At 5, yeah. If this x here is 5, I get 0 in the denominator, which is considered undefined. So let's go over here to x equals 5, and we see that we have a hole. So it is discontinuous at that particular point. What kind of discontinuity is this? Removable. It takes a single point. What is that single point that I would put in there to take care of the problem? What's the single point? What is a point? Has two values, right? It has an X value, which is your left right value, and an up down value, which is your Y. What is the point that I could put in there to take care of the problem and it wouldn't be discontinuous anymore? Louder? Yeah, 5,9. Do you agree? 5,9? That would take care of the problem and it wouldn't be discontinuous anymore. So this is discontinuous because of a removable discontinuity, right? You could call it a point discontinuity, but I want you to get used to this removable discontinuity because that is more common in the AP curriculum. Okay, let's do another one. What if I have something like this? Y equals X over the absolute value of X. Do I have discontinuity? Where? X equals 0. What kind of discontinuity is this? It's a jump discontinuity. I'm going along here and I'm at Y equals -1. And then all of a sudden at this point, bam, I just jump up to this other, I teleport, right? I teleport from one point to the next. So that would be an example of my jump discontinuity. Now I don't have one for oscillate off the top of my head, but I could probably try to create one. I have sine of X and then this just seems to oscillate up and down. What do I do to the sine of X? What kind of transformation do I do so that I squish all these together so it's hard to tell what we're converging on? What do I do? Is that my A value, my B value, my C value, or the D value? It isn't the A, isn't that my stretch? So 2, 3, 4, 5. I want to squish everything together so it oscillates so close together it's hard to tell. What's that? Is my B value. Is my B value, would I make my B value big or small? If I want to squish everything together. Isn't, when we have parentheses, isn't it we have this funny business? So would it be small? If I put in something small like, I don't know, 0.5 or 0.4 or 3 or 2 or 1, what's the problem? We have that funny business, right? Anything in parentheses, we have that funny business. So we have to do the opposite. If I want to squish everything, my B value has to be what? It has to be big. It has to be big. So let's put in, well, first let's make this an amplitude of 5. And then I'm going to put in, I don't know, 1, and then how about 10, 100, is that? I don't know, 1,000, 10,000. Oh, you can't tell anymore anyway. So when X, looking at this, when X approaches 1, what does Y approach? What's that? Yeah, you can't tell. You can't tell. And that's the point. Because you can't tell, we call this an oscillating discontinuity. We don't know. We don't know where the line, I don't even know where the line is anymore. I don't even know what it looks like. Because it's just crazy up and down. So we would say in this case, it would be an oscillating discontinuity. Okay. Are you confused? Fairly easy so far? Okay, let's do some examples. Here's my graph. I have a graph that looks, Riley's thinking Mr. Alt doesn't have to be perfect. Riley, it needs to be perfect. There we go. So let's mark some values here. We'll say that this is 3 and this is 6, and then we'll say that this is 3, 6, 9, 12, 15. And then I have a line that looks something like that. And then something like this. What do you think, Riley?
Oh, so we have jump discontinuity.
Oh, I just meant, how do you think about my perfection?
Oh, okay.
It's not perfect, but I'm trying. And mostly I'm trying because I feel like, you know, if I mess up, then it might, I'm concerned that some of the meaning might be lost. So we have this graph here. Now, what if I ask, I want to know, can you guys see where we have an open circle and closed circles? Is it obvious, or do I need to fill some of these in a little bit better? It's fine, okay. So say that my question is, on what interval is f of x, we'll call this our graph of f of x, continuous? When I talk about on what interval, am I talking about am I going to describe the interval in terms of x or y? X, yeah, yep. I'm gonna refer to this as my x value. So what are my intervals? So it says on what interval? You can see that there's going to be more than one, it looks like. What is my interval, or one of my intervals? Catherine, what do you think? I'll start out 0 to what? I'm going from 0 to what as continuous? 0 to 3. Okay, I agree with you. 0 to 3. So we're saying that all this interval here is continuous. Does everybody agree? Yeah, I agree with you. Yep. Catherine, what about my endpoints here for 0 to 3? Is 0 included? Yeah, it looks like it's included. It's a closed circle there. So I'm going to say it's included with a bracket. And what about 3? Is 3 included? No, we have an open circle there, an open circle indicating that it's not included. So I'll use a parentheses instead. Fernanda, what's the next interval? Three to what? 3 to itself? So are you referring to this point right here? This is 3, 3. That's the point. But I'm actually trying to indicate an interval. I'm trying to say, I'm trying to identify where the graph is continuous, and remember, the non-rigorous definition of continuous is by drawing a curve or a line without lifting up your pen. Once you lift up your pen, then it's no longer continuous, right? So when I say on what interval is f of x continuous, I want to talk about where does it look like the pen was not lifted up. So from 0 to 3, for this interval right here, it looks like the pen wasn't picked up. Yeah, from 3 to 6, I agree with you. From 3 to 6, it looks like from 3 to 6. Is 3 included? Yeah, I agree with you. What about 6? No, so I'll use parentheses. All right, cool. Kayla, what about the next interval? From 6 to 12. Okay, 6 to 12. Is 6 included? No. So I'm going to use parentheses, and is 12 included? Would it change things? Would you change your opinion on whether this was continuous if I put a dot right here?
Because wouldn't that still be considered discontinuous?
Yeah. Oh, No, this wouldn't be a jump. This would actually, because it's still removable. And you're still looking at one point that needs to be replaced. Does it look like, can I draw, if I have a hole right here, can I draw it without lifting my pen? No. So this is still going to be continuous. I would have to, the only way I could fix this is if I took this dot here. They're not going to let me pick it up. If I took this dot here, I wonder if I can just make that transparent, and I moved it down here. That's the only way I can fix it, right? Emerson, what do you think? Yeah, so it doesn't, if it's over here, if it's up here, I do have a value. Remember the definition. So remember the definition, our rigorous definition of continuous. A rigorous definition of continuous would be this, that the limit in this case, oops, the limit as x approaches, in this case, 6 of our function of f of x equals f of 6. Is that true? What is the limit as x approaches 6 of f of x in this case? What is this? Looking at our graph. Kyle, what do you think? What is, this is 6. I don't know if you can tell that that's 6. Maybe I just made it worse. Kyle, what is this? If that, what's my limit as x approaches 6 of my function? Okay, that's fine. How about Chris? Chris, can you tell? It is 3, yeah. Remember, Kyle, when x gets incrementally closer and closer to 6, what does the y get incrementally close to? Do you see, Kyle? What does the y get closer to when x gets closer and closer to 6? This is my x. What does y get closer to? It gets closer to 3. Yep. So this is going to be 3. Well, what is f of 6? Yeah, f of 6 is 6. Are they the same? No, they are not the same. In this case, they are not the same. So it is discontinuous. It is discontinuous. That is a rigorous definition. Okay. Okay, I think there we go. Let's get rid of that. Let's talk about what type of discontinuity we have here. So when x equals 3, what kind of discontinuity do we have? When x equals 3, let's make sure that we can see everything. When x equals 3, what kind of discontinuity do I have here? Yeah, does everybody see it's a jump? It looks like we're teleporting from one end to the next. We have a jump discontinuity. We get a jump discontinuity. What about when x is 6? We get removable. Why is it removable?
Because we plugged in 600.
Yep. If it's a single dot that's missing, then we call that a removable discontinuity. Are we good with this? Emerson, you good? Emerson, you don't look that confident back there. Getting nervous. Yeah, you think I got it? Okay. Emerson, what are the 4 different types of discontinuity?
Removable.
Removable?
Infinite.
jump, infinite,
and oscillate.
and oscillating. Yep, those are the 4 different types of discontinuity. All types of discontinuity can fall into those 4 different categories. All right, so what if let's consider, okay, so if I have, let's consider our transformations. What does this look like as a transformation? What's left?
From, yes, from just the x square root of x, shift 3 left.
All right, so what does the square root of x look like?
Like, that's the origin and like,
Yeah, that's exactly what it is it's literally a half of a parabola. If this is y equals x squared, then then we have this as y equals the square root of x and y equals negative the square root of x. We literally have a half a parabola that's been flipped over the y equals x, the y equals x. So we have this little piece. You, Emerson, you drew it in the air. I absolutely agree with you with what it looks like. And so I understand now what you mean when you said go left. So we have y equals the square root of x that looks something like this. Emerson, can you try to explain a little better what you mean by going left? Or why? Why do I go left?
well, since it's in the function, it's gonna be horizontal.
Mhm.
But it's not like multiplying x, it's just like adding to the sum. Since everything's backwards in the function.
Perfect. Yeah, Emerson, good explanation. So Emerson said that we are going to be shifting to the left and not to the right. One, because this is in the function, not to the function. In the function is always horizontal. And then we have these weird parentheses. The parentheses give us with that funny business. So we end up with a shift 1, 2, 3 to the left, not to the right. And then our graph is going to look something like that. Can we tell at this point, Chantel, the green graph, which is the square root of x plus 3, what the interval of continuity is? What is the interval of continuity? 3 to infinity? Is it 3?
Or -3.
-3 to infinity. Is -3 included? Can I plug -3 into this? What is -3 plus 3? What's the square root of 0? So whenever we see a square root, we're literally asking what times itself gives us that number. It is 0. So it is included. It is included. So we include it with our brackets here. And then infinity is not a real number. So for infinity and negative infinity, we always use parentheses because we're not saying it's a stopping point. We just, whatever the largest number is, infinity is larger than that. It's not even a number, it's a concept. So we have, this is our interval of continuity. The interval of continuity. Interval of continuity. All right, let's try another one. What if I have, let's do g of x. If I'm going too fast, let me know. I always hated when a teacher moved on and it's like, oh, I'm about to write that down. No. All right, I have 1 over x plus 2. And the same thing, I want to know what is the interval of continuity. What does this graph look like? What function family is this? That's rational. This is part of our rational function family. A characteristic of rational functions is asymptotes. Do I have any asymptotes? I have two asymptotes. I have a vertical asymptote and a horizontal asymptote. Where are they? Yep, the vertical asymptote is at -2, because if x is -2, then I get a 0 in the denominator, which is undefined. So we do have that one vertical asymptote right more or less here, okay? That is at 0, y equals 0. I agree with you. How did you get that it's y equals 0? Okay, so remember our n. Remember when we did we have all rational functions are polynomials over polynomials. So I have something like this: a times x to the power of n plus blah blah blah. The other stuff doesn't matter when x is really large. And then I have b times x to the power of m plus blah blah blah. The other stuff doesn't matter. The other terms don't matter. Only the leading term does, the largest term, the one that indicates the degree of that polynomial. Because when x becomes large, the other values are left behind. Now remember those three different conditions, right? There are three different conditions. One is that n is less than m, n is equal to m, or n is greater than m. So what happens, do you remember, Eleanor, what happens if n is less than m? Yeah, the horizontal asymptote is always going to be 0. And think about it. If n is smaller than m, then when x becomes large, this becomes a huge number, leaving this other number in the numerator behind, and so you just converge on 0. All right, what about if n equals m? If both of these exponents equal? Yeah, then your horizontal asymptote is going to be y equals a over b. What about if n is greater than m? Yeah, it doesn't exist. It just the numerator is so much larger than the denominator, you just take off to infinity. It just grows and grows and grows. So we have the horizontal asymptote is none. It's none. We don't have one. All right. So what do we have? What case is this? Is that n is less than, n is equal to, or n is greater than m? All right. So you said it's at n is less than. So what is the exponent for the numerator? It'd be 0. Yeah. What's x to the power of 0? It's just 1. Yep. And what about the denominator? Yeah, just 1. Yeah, so we can see that the case here, n is less than m, which means the horizontal asymptote will be 0. So we're going to just draw our horizontal line here at 0. So the definition of an asymptote is convergence. We have a vertical and a horizontal asymptote, which means we have to converge, which means we either converge like this, or we converge like this, or we converge like this and we converge like this. Do you see that there's not really any other choices? Because of these asymptotes, we have to converge. My graph can't go like this, because then I'm crossing my asymptote. Does that make sense? Why we either have this or this, or we have this or this? Why can't we have both? It's not a function. It violates the vertical line test. So it can only be one of these, the top or the bottom, and then one of these over here on the left-hand side, the top or the bottom. How do we determine that? How do I know which one it is? Riley, how do you tell which one it is? Over here on the left-hand side. Is it at the top or the bottom? How do you figure that out? Well, let's plug some value into it. Let's plug in -3. If I plug in -3, that'll tell me if we're above the horizontal asymptote or below. Does that make sense? Okay, so what number do you want to plug in? What's an x value to the left-hand side of this vertical asymptote? Okay, -5. If I plug in -5 here, do I have a number? Is my y value above 0 or below 0? It's below 0. So so do you see that it has to be this then? Because of the definition of an asymptote, we have convergence. All right, now we have to figure out something over here. So Riley, how would I figure out what it looks like over here, whether I have this graph or this graph?
Same idea.
Yeah, same idea. So what value to the right of this vertical asymptote? What's an x value to the right of this vertical asymptote that we can plug in?
Let's go with 5 maybe.
All right, let's just go with 5. So 1, 2, 3, 4, 5. If I plug in 5 here, does that put me above the? Is it larger than y? Is it larger than 0 or is it less than 0? Yeah, it's positive. So it's going to be, so our graph has to look like this. Yep. Although let me get rid of the other mess here. Okay, so it's going to be like this. Now we did a lot more than we needed. It didn't ask us to graph it. Although it doesn't hurt to understand, it gives us a deeper understanding of the whole procedure. I'm asking to find the interval of continuity. What is the interval of continuity? Chris, what do you think? What is the interval of continuity? Because -2 is not included. Okay.
And then it would also be -2 to
Yeah. Chris, what kind of discontinuity is this? Yeah, it's an infinite discontinuity because we're going to infinity on those sides. Yep, correct. The next couple of problems we do, this is directly, the next couple of problems we do, these are problems that were on past AP tests. And I'm going to try to incorporate as many problems along the way until May of problems that were on past AP tests so that we get lots of practice. I feel that the more practice we get with the legitimate problems, the better we will get, we'll do on the test. All right, so the directions, I want to fix the removable discontinuity. And I have our graph looks like this. Does this equation have a removable discontinuity? How did you get 3? So we have a hole in there. So and this would be a multiple choice question. And so this would be, it's actually written as a piecewise function. And so I have something like this. I have f of x equals, and then we have this squiggly bracket. And then we have this x squared minus 9 over 3 for all x values that are not 3. Now the question is, there's some value here for when x does equal 3. The question is, what?
X
f of x means your y, right? So I have two equations here. My piecewise is made up of two equations. One is this one, which is written here. And then the other one is here. So this is my y value. Well, where's my x value? My x value is here. So the question then is, we know that we need to fix the problem, to fix the removable discontinuity. X has to be 3, but what's the corresponding y value? X has to be 3, but what's the corresponding y value? Didn't we do this already when I had something like this, the limit as x approaches, in this case, 3 of x squared minus 9 over x minus 3? Don't we have to find the answer to this? Because the rigorous definition of continuous means that that has to equal f of 3, right? Wasn't that our rigorous definition? So let's find this and then make this equal to it. How did we find the limit of this? Yeah, let's factor. Let's factor. When I factor this, what do I get? All right, so you see this as a difference of squares. And because it's a difference of squares, what's our rule for a difference of squares? When I have a squared minus b squared, then this becomes factored to be what? A plus b, and Riley?
Oh, A minus.
And a minus b. So this is our difference of squares here of x squared minus 3 squared. So our factored form is going to be what? One more time, Riley. I know you said it like 3 times, but one more time.
Plus 3 and x minus 2.
There we go.
And we cancel out the denominator.
We can cancel out the denominator, and that gives us this x. This becomes x plus 4. Okay. Oh, sorry, x plus, yeah, x plus, oh, how did I get the 4? Huh. I'm just messing up all over the place. Let's try that again. You said it, and then I wrote it down wrong. Sorry about that. X plus 3. And so this,
Would be x minus 2.
let's try that again. X. Man. How about that? Riley, are you good with that?
Yeah, we
Okay. Okay, so this becomes x plus 3. Now what? How did we get what the graph was converging on when x approached 3? Emerson? How did I get what x converged on? Or what, sorry, let me say that again. How did I find what y converged on when x approached 3? Okay, so I already factored, so now what?
And then you can plug in 3,
To get what?
6.
Yeah, the answer is 6. The answer is 6. So what does this mean? I'm going to go to Desmos and I'm going to type this in. Just move this up here. Oops. There we go. All right, here's my piecewise. I have f of x equals, let's have a numerator and denominator, x squared minus 9 over. How did we get 3 there? It's x minus 3, just being sloppy, I guess. And then what that means then, and then I have my other equation of y equals 6. So let me fix that. I'll fix it later. So we're going to use this equation here of x squared minus 9 over x minus 3 for all x values except for when x equals 3 right there. And then just for 1 point, for when x equals 3, I'm going to use this equation to fill in the hole. That makes sense, or is that confusing? I don't know how I messed up on that. I'll have to go back and listen to myself when I put that in. Okay. Do you want me to explain this again, or are you good? Yes, question.
So just answer that like as a function, like how would you write out the answer?
So this is the answer. It is a piecewise function. And this piecewise, this piece here for values when x is equal to 3 only, that just 1 point, will give us this equation here, except for we're only using this, what is it, blue graph? We're only using this blue graph for that single point when x equals 3, and that fills in the hole. So it's Ellie, right?
Yeah.
So Ellie, so when x equals 3, right now we have a hole. So for that single value, that to fix the removable discontinuity, when x is 3, y is 6. That takes care of the problem. Okay, and in fact, if we're going to do a couple like this, and so since we learned through repetition, this will give us a lot of good repetition. These are problems from past AP tests. So given f of x equals, yeah, this squiggly line, maybe I'll move this down a little. And I have x squared plus 5x minus 24 over x minus, getting sloppy there, x minus 3. This is, and then we have this f of x equals k. We're going to use our first, the top part of our piecewise for values of x that are not 3. And then we'll use the other piece of the piecewise when x equals 3. And I want to find the value of k to make this continuous. Find the value of k to make f of x continuous. Josh, any ideas?
I'll start up. Yeah, I think factoring would be a good idea. So remember that the limit as x approaches 3 of this x squared plus 5x minus 24
over x minus 3. If it equals f of 3, then it is continuous. So we need to find out what this is to make this equal to it. So Josh said, let's factor. So let's go ahead and factor this. So when I factor this, is this factorable? To what?
X minus 3
X plus 8 over x minus 3. Now what?
You can cancel out the X minus 3.
Okay,
And then now you just have X plus 8, so you can just plug in 3 of that.
to get,
So you just get 11.
you get 11. So yeah, so if k equals 11, then it's continuous. Miguel, do you want me to put this in Desmos? Would it help to see this in Desmos? Or do you want me to explain it again? What would be the best way to help you understand this better?
I just don't want to see it in decimals.
All right, let's do this in Desmos. So we have our equation of f of x equals, let's make sure we have a numerator and denominator, x squared plus 5x minus 24 over x minus 3. And we know that there's a hole here when x is 3. Let's see whether we have that right here. Miguel, do you see the hole? Now you can just look at this by inspection. You can see that the single dot that will fix the problem is what? 3 comma 11. Here's my 3 comma 11. Isn't your f of x, isn't that your y? Isn't this your y then? Yeah.
So I got a quick question.
Yeah, Miguel, what is your question?
The X equals 3, we use that in the factor form to get 11.
Yeah. In fact, this is what we did. And I think, what was it, 2.1? When we first started limits, was what I wanted you to do. We figured stuff out like this. And one method for figuring this out was, well, here's one method. We could write this out of here's my x's and my y's here. And then let's try to think of if I have, I don't know, 2.9 and then 2.99 and then 2.9999 and then find the corresponding y values, what I'm getting closer and closer and closer to. That's one strategy. Another strategy is that we can factor. We can factor this and eliminate stuff. That was another one of the methods that we learned. And then if it turns out to be some type of trigonometric limit, then we have to use our cards. Remember, like the limit as x approaches 0 of, what is that one? Anybody remember what this is? The limit as x approaches 0 of sine of x over x. Yeah, just 1. Yep. Do you remember what the limit as x approaches infinity of this, what that is? 0. Yeah. What's the other card was when x approaches infinity of cosine of x over x. What's that one? It's also 0. Yeah, those are the ones that you have to memorize so far. I think we have 4 cards now, total of 4 cards that you have to memorize. Those 3, and then the other one that I want you, if you haven't memorized this so far, you should have this memorized. You should learn this, the sooner the better. Sine squared of x plus cosine squared of x equals what? Yeah, it's just 1. That's our Pythagorean identity. That's something you do need to know. Okay, those are our 4 cards. Here's 1 card, here's 2 cards, here's 3 cards, or flashcards, right? Flashcards, and here's our 4th one that we should know. All right, so let's do another one. Let's do another one. So Miguel, guess what? You're on the hot spot. You're on the hot seat. So given g of x equals x squared over x plus k. Now we're going to use, oops, sorry, I wrote that down wrong. I completely wrote that down wrong. So equals the squiggly bracket of x squared for values of x that are less than 3. And x plus k will be used for values of k greater than 3 and equal. So I want to find the value of k that makes g of s continuous. What is the value of k to make g of x continuous? Does it help if we drew some type of image for understanding? What is this first function here? Yeah, it is a parabola. I agree with you. It's a parabola. We're going to use this parabola for what values of x? Yeah, anything less than 3. So 1, 2, 3, something like this. Well, what's the corresponding y value? What is it? 9. Now I need to try to find some line. What kind of function is this? What kind of function is this? It's linear. Do you see that if my linear doesn't match up right, it's not going to be continuous? So I need to try to think of some, or even up here, right? That's not going to be continuous. I need something that starts here and continues here. How would I do that? Okay, you could think of transformations. I know I have some linear function with some linear function of y equals mx plus b with what solution? I already know one solution. What has to be it? Yeah, 3, 9. Can you think of a linear function that goes through this point? How would I do that? Can I think of some linear function that goes through this point? Okay, so I have y equals x plus k. I think you said it, but how did you get it? How do I find k? Yeah, this is my x. This is my y. Plug it in. So I have 9 equals 3 plus k. Now what? Subtract 3. That gives me k equals 6. Yeah, you were right. So the answer is k has to be 6. K has to be 6 to make that work. So that it lines up. Miguel, do you want to see this in Desmos again? Okay. Let's look at how this looks in Desmos. So I have g of x equals x squared. And then my other one is I have y equals x plus 6. So let's make sure. Copy that, undo it. We have to make this continuous. And right now, our first equation for x squared for values of x that are less than 3. Let's zoom in on this a little bit more. So that would be the parabola for all values of x less than 3. So I'll just erase this piece here. And we don't use the parabola after 3, so I'll erase that here. And then for the parabola, we have a hole here. So I'll do a little circle here. Like maybe like that. And then we use this equation right here for values of 3 included, and it's continued. So I'll just fill that back in for the other piece here. So that's what it looks like. That's what we're saying with, it's this piece here, this piecewise right here, that is implied by this piecewise here, by the piecewise equation. Kata, question? Are you confused? You're good? Okay. So we went over 3 different examples like this that are, seem to be common in AP, past AP tests. So hopefully that will be helpful. So let's do another. So now I want to talk about the properties of continuous functions. These are the properties of continuous functions. So if f and g are continuous at some value of c, then f plus g is continuous at x equals c. If f and g are both continuous at c, then f plus g will also be continuous at c. So if I have some function like, let's see if I can, I don't want to, for those of you who are still writing, I want to make sure I'm sort of out of the way. If we have 2 functions, like, even these 2 functions, right? We could look at these 2 functions and then we would say, well, at 5, the green parabola is continuous when x is 5, and the black line is also continuous when x equals 5. Okay, there. And because they're both continuous at x equals 5, then if I add these 2 functions together, that would give me what? X, that gives me y equals x squared plus x plus 6 is also continuous when x equals 5. X equals 5. Oh, it's the wrong one. X equals, it's also continuous there. Okay. Does that make sense what I'm saying? If f and g are both continuous at some value c, then if I add those 2 functions together, that new function will also be continuous at c. All right. It's also true that if I subtract those 2 functions, this will also be true. If I multiply these 2 functions, it will also be true. If both of these functions are continuous at c, and I multiply those 2 functions, the resulting function will also be continuous at c. Now it's also true. So, and then if I have if I have some constant of k of x, or k of g, so this is just some scalar, right? Isn't that our vertical stretch? If I have some vertical stretch, then that's also a vertical stretch. If for some value of x, if it's continuous for both of those functions, then that same value will be continuous even if I multiply by some scalar and have some vertical stretch. So k is a constant. I'll just do this. K is a constant. And it's also true if I divide, if f and g, provided that g of c is not 0. Remember, C is this value of X. One more thought and we're done. Emerson, how are you feeling? Do you feel like it's too much math or just about right? Just about right? Cool. Nice. I didn't give you a third option. The other third option was it's not enough math. Okay. All right, so here is the last one. The last idea. Are you guys still copying? Miguel, you said you watched part of the video today.
Yeah.
Did it-
about 5
did-
minutes in now.
Oh, just 5 minutes in? Oh, okay. I was just going to check to see if this was similar, if you felt like that some of the stuff was similar. All right, the last one is the intermediate value theorem. The intermediate value theorem. Intermediate value theorem in a nutshell. If I have some point of B and some point of A that are connected without picking up your pen, so they are continuous, then all of the X values between B and A are included, and all of the Y values are also included. So if we have a continuous curve between points B and A, then all X values between the 2 points That's awful. Points and all the Y values and all the Y, that Y, the Y values between the 2 points are represented. On the curve. I'm sorry, I'm not a huge fan of this theorem because it seems so intuitive. Why wouldn't that be true? If you have 2 points and you have a continuous curve between the 2 points, why wouldn't all the X's and all the Y's be included?